far back as 1920, I conceived the idea and the possibility of when the causative agent of malignancy, so-called cancer, would be discovered and found and proven, that it would be caused by a microorganism. Of course, reception that I received that far back from the medical profession and scientists was nil. But I kept at the work, and I succeeded in eventually isolating a virus. First, I began sectioning tissues of every known type of malignancy. I sectioned over 20,000 of those, cut them down with a special microtome to very thin. Some of them were only a micron in thickness. I studied those under the microscope, and I eventually built my first high-powered microscope for the purpose of analyzing and checking those sections. The only result that I obtained over all those years was I succeeded in developing a very excellent technique of tissue preparation, but I never found an organism that I could say was the causative agent of malignancy. I went through with this, and then I developed other instruments of greater amplitude of magnification than the old original number one, which was very lacking in resolution beyond about 8,000 or 9,000 times. It was a lens microscope, and all of the air was excluded from the body and replaced with glycerin. The lenses were homogeneous with glycerin all the way through the whole thing, and the result was that in allowing the rays to separate and not cross in the interference band of reflection, such as they do in the ordinary standard tube of the regular research microscope, we held them apart, we separated them, and then brought them back together and picked them up again at a needle point. But, as I say, the resolution of this instrument beyond about anywhere from 9,000 to 10,000 times dropped off decidedly rapidly. We could go up on some occasions, on some preparations, up to 17,000 times, but we didn't consider the resolution anything out of the ordinary beyond about 8,000 or 9,000 or 10,000 times, depending entirely upon the specimen we were examining. With the results that those tissues gained us absolutely nothing. And as I say, I built other microscopes beyond this one. But that instrument we used up until 1931. With that instrument, Arthur Kendall and I, working jointly in the Pasadena General Hospital, succeeded in isolating what we classify the first filterable form of bacteria ever seen. It was isolated from the Bacillus typhosus from cultures that Dr. Kendall brought from his laboratory in Northwestern University in Chicago. And we succeeded definitely in isolating a filterable form of that bacteria. Now, these filterable forms are very minute in size. The smallest of all is the one from the BX, which we isolate from cancer. We have never made a positive claim that that is the causative agent of cancer. But that is the smallest, and is less than a 1/20th of a micron in dimension and highly motile. We succeeded in isolating this organism, this BX, using a Kendall media. It's known as Kendall media. It's made of a desiccated pig intestine, dehydrated down where it requires about 10 gallons of the original raw gut when it's desiccated, and run through the extractor and dehydrated to make about 1 pound of the original material. Now that is placed in a tube. We use about 4 grams, and then we use 10 to 20 cc's of a tyrode solution. It's a chemical series of salts. Now that is what Kendall used for the isolation or bringing out this Bacillus typhosus in the filterable state, which is published in the Californian Western Medicine in 1931, our joint report on that. Now, these organisms, again, before we go farther, they cannot be stained with the aniline or acid dye stains that's used in the ordinary technique and method of staining tissue sections or even bacteria. Now, those organisms are so minute and so delicate that They have to be stained with a frequency of light. Now, after we built our first high-powered microscope, we had to build an illuminant unit to be able to see these different types of organisms and different types of tissue also. So, we had to build this particular unit. We built a unit which I have a patent on, a special lamp that will produce 2,000 candle power on a needlepoint of beam where it comes through the condenser. But between this source of illumination and the so-called substage condenser, we have a pair. On the universal microscope we have 4, but we use a pair of rotating wedge-shaped quartz prisms. They're circular and they're wedge-shaped. And by rotating those, we bend the beam of light, that's what we term the neutral or core beam of the illuminant unit, at different angles of incidence, so that it strikes the object under examination at different angles of refraction. There we see these particles at a different refractive index, and every one of them is entirely different. For instance, we find that the Bacillus typhosus, in its filtrable state, is a beautiful turquoise blue body. We see them swimming through the field. They're highly motile. And incidentally, if the organism, the bacteria, is a motile bacteria, in most instances the virus will be motile or highly motile, and vice versa. So we see these beautiful turquoise blue bodies swimming through the field. With that, we can differentiate